start. Hello everyone, welcome to Handmade, Hero, the show where we code a complete game live on Twitch from scratch, no libraries, no engines, so that we know everything that goes on. Nothing hides from us. We are in there with the flashlight, looking under the bed, scaring the monsters away. Even if they're particularly scary monsters, we just generally are completely unpersuaded by that because we're kind of big and gnarly and have hairy fangs ourselves. Anyway, if you would like to follow along with today's episode and you have pre-ordered the game on handmadehero.org, please don't forget to download the source code from the link in your email, and you will want to unpack day 94's source code. I believe that's correct. Day 93's source code, so that you can do day 94, which is what we're on today. That is all you should need to do, and then you will be exactly where I am. So, assuming that is all good with you, I would like to say a few words about where we left off, just so everyone is on the same page. So what we did last week is we basically started our renderer, and we did a bunch of stuff on it. As you can see in the middle of the screen now, kind of ridiculous. We don't really have an excuse for why a tree would be rotating in place other than it was our test bitmap. And you can kind of see right now that we've actually implemented texture mapping so that we can freely rotate and scale things. And we did it with bilinear filtering. So you actually get kind of a nice smooth version there as well. Now, we're going to talk about something today that normally I don't think I would really talk about, to be completely honest with you. But we're talking about it at the behest of Wan Chun, who made me promise that I would talk about it on the stream. So here we go. It's gamma correction. And somebody actually asked about it in one of the Q&As. They didn't ask for it by name, but I believe they were asking about it sort of indirectly. And so at least we know there's one person out there who wanted to know about it, and so it won't be completely useless. Let's put it that way. And it's very near and dear to Juan's heart, apparently, so he really wanted everyone to know. So we're going to do it. And what the person who asked in the Q&A, they were saying they had seen some video about how color blending is done incorrectly on computers. And he said, like, since you're doing this all from scratch, you have the opportunity to do it correctly. So one thing that I should point out is when they say that blending on computers is done incorrectly, they're actually just talking about paint programs. Games actually do blending correctly. Games, we have been doing blending correctly for a long time, actually, for probably about 4 years. Gamma-corrected pipelines have been in the works, probably since Half-Life 2, certainly in The Last of Us, and what was it called? Uncharted 2. Those were all using gamma-corrected pipelines so that they could specifically do color blending correctly always, right? And so games have actually been way out ahead on this. And yes, it's true that people like Adobe and stuff may not be doing any of this stuff correctly. And that's, I think, what the video that you were referring to was talking about, because they don't do stuff gamma corrected in a lot of places, and there's plenty of art packages that don't do gamma correction properly, but games are not really one of them. Maybe 2D games don't do it as much because it doesn't really matter, but certainly 3D games where it's very important for lighting and for HDR, high dynamic range imaging, which games use nowadays, that stuff is really where you got to get your gamma correct. So games actually have been doing gamma correctly, and I'll I'm certainly not a gamma expert, but I'll try to give you what the idea is so that you can be aware of it and maybe do some reading on your own, and then I'll show you how we can sort of implement it a little bit in our software rasterizer. In our hardware version, we'll do it 100% correctly because it's actually really easy to do correctly in there. 100% is probably a little wrong term, but very close to 100%. So basically, here is a chart. I don't know if you guys can see this. In fact, maybe I'll go ahead and just play with this camera setting here for a second. Let's see if I can do this here. So if I pick webcam, right? Can you guys see this chart? Do you see what it says there? So at the bottom, right, on the x-axis, it says gray level, right? And that is like the pixel value. Okay, that's like what we're sending, like 0 to 255. Okay, and then on the y-axis there, let me see if I can get a little closer. On the y-axis, it says brightness in candelas per meter squared, right? So that is actually, gosh darn it, we need to turn off our assertions. hold on a second. I need to turn off these assertions. I left them in there so we would know, but okay. So candelas per meter squared is the brightness that the monitor is actually putting out there, okay? And what you can see is this does not form a line, right? It forms a curve. It forms a curve, not a straight line, which means that as you change the values that you're sending to the monitor, the pixel values, they actually get a lot less bright for every increment that you use when you're down at the low end, right? So down in here, if you add one or two to your pixel value, it actually doesn't get much brighter, right? Whereas on the other side, like up here, when you add 1 or 2 to the value, it actually gets significantly brighter by comparison, right? Does that make some sense? That's what monitors do. And so basically, oh dear, the focus has all gone crazy. Hello, focus. Focus on me. There we go. Let's go back to the programming screen there. Okay. So that curve is how monitors operate. We could go into the history of why they operate that way, but honestly, I'm probably the wrong person to tell that. Let's see here. I got to start a new day so we can do some drawing on the blackboard. So here we are at day 94. Oops. Day 94. Gamma. And as you can see, the curve on that thing, here was candelas per meter squared, which is basically like a measure of brightness, just like it's, candelas are a measure of brightness. Per meter squared means, normalized to an area, how big of an area that it's coming out of the screen, right? And here is the actual pixel value, it was down at the bottom, right? And you notice that thing went like that, right? It kind of like had a lot of resolution down here, so you could change a little bit and have it not change very much. You'd have a lot of control down here, and then you had very little control up here. So you have like, high control down here and low control down here, right? And the reason that they did this, as far as I know, is, well, actually, to tell you the truth, I don't really know the reason why they did it. I'm not going to pretend I know. You should go read about it. I believe that the reason it stays this way is because your eye is more sensitive to contrast in darker areas than it is in brighter areas. I believe this is just an aspect of the human visual system that basically says that if you have two bright colors, color we can take out of it, two bright gray values next to each other, and two dark gray values next to each other, a small difference in the dark gray values will be much more evident to your eye than a small difference in the light values, right? So basically you can see differences here less than you can see them here, right? So they put more control in there so that you'd have more ability to specify finer shades of those dark grays, instead of putting it linear where you'd have the same control up here, which just wasn't that useful, right? So why do we care about this at all? Why are we even bringing this up? Why does Juan care about this, right? So why does Juan care? And why does the person who asked the question, what was the video they're referring to? Why did the video care? So the answer is because maths is the answer, right? If this is the question, maths is the answer. The problem with this curve is that a lot of the things that we want to compute are in brightness terms, right? So if I, for example, want to do any operation that I might want to do in color space, right? Including all of the ones that we've currently done. For example, just yesterday we did the bilinear blend, right? We took 4 pixel values, right? A, B, C, and D, and we said, let's make a little imaginary rectangle, well, square in this case, out of these. We will blend between A and B linearly. We will blend between C and D linearly, and then we will blend between the result linearly in order to get what the color should be here. Now, implicit in all of this was us saying this word right here, linear. We were expecting that as we blended between A and B, that if we were to, for example, go halfway in between them, we would have a result that looked, let's say, half of A plus half of B. That's what we wanted it to look like. So if this was, say, 25% the brightness that the monitor could output, and this was 75%, we wanted this to be 50%, right? Does that make some sense? Another way to say that might be if this was 0% and this was 100%, we want this to be 50% as well, right? Any balanced range on either side, we want it to come out in the middle of those two, right? But what's actually going to happen when we do that blend? Well, here is where we're doing the blend. We're doing the blend in pixel value space, right? And so let's take a look at what happens here. And unfortunately, it may not come out that great because, I didn't draw the world's most perfect diagram, right? But here are the two endpoints of the pixel value curve, right? So if I were to do that bilinear blend, again in the space, or just a linear blend in the space we just talked about, in pixel space, in that color space, I would get here as my 50% value, right? This is 0, this is 255, I'm going to get 128, it's going to be right there, right in the middle. Well, what brightness did I did? I blended black with white, essentially, right? As white as the monitor can do and as black as the monitor could do, that's what I blended. And I ended up with that. That is like dark gray, right? It's nowhere near half the brightness. Half the brightness would be up here, right? So the result of not taking gamma into account is that all of this maths break. They all break because we were doing them in a space, and the math is certainly correct for that space, but our understanding of what that space meant is wrong. We thought we were getting a brightness blend. We're getting a blend in some space that has nothing to do with the brightness, right? It's a totally different space. And when we map it to the brightness, we get a completely wrong value. Does that make sense? Hopefully that makes some sense. So if we actually want our math to properly be able to blend things together, what we need to do is undo the effects of this curve, right? And unfortunately, when you think about it, you're like, well, there's no way to really undo the effects of this curve at some kind of fundamental level because the monitor outputs this curve. And there ain't no way you're going to change the monitor. The user already bought the monitor, and you can't really do anything about that, right? So what we need to do is essentially account for the fact that the user bought this monitor and take into account all of the ramifications that go with it. Now, when I say user, unfortunately, I don't just mean the player. Okay, that is one person, but there's another person that matters here, and that is the artist. So both your artist and your player have monitors, and those monitors look like this. So when the artist makes an image, they are actually making the image in that gammaed space, right? Assuming they're using Photoshop on this default settings, I believe it is called sRGB, is the Adobe standard, which is sort of a modified, it's basically that gamma curve, it's a little tweaked, but that's basically what it is, right? And so the artist actually made an image that was in that space, okay? They painted it looking at the monitor, so they've tuned it to be in this space already. And so when we blend it to the screen, if we didn't do any math on it, it would be correct, right? So we sort of have a case where our input, right, is in this space. This is in sRGB space, right? And our output also needs to be in sRGB space because the monitor is going to do it, right? The monitor needs to see sRGB. The artist makes sRGB. So if there's nothing in between, we don't have to worry. But the instant that we do anything to color values and expect them to be linear, such as a bilinear blend, which you've already seen we need to do for texture mapping, in here where we are doing them, where the maths happen, we have a problem. So what we need to do if we want to correct this problem is we must do the maths in a linear space. We want to take them out of sRGB space. Actually, I should have drawn that a little bit differently. Maths, linear. We want to take them out of sRGB and put them into a linear space. Then we want to take them from the linear space and put them into the sRGB space again when we are finished, right? So that is actually the gamma correct pipeline, and it is what AAA games do. It is what a competent engine does. If you went and used the Unreal 4 engine, I'm sure it does it that way. I assume Unity does now. I don't think they did originally, but with their photorealistic shader updates they did, they would have had to have done this, so I'm assuming they do it now. And really, anyone who knows what they're doing does this. It's very easy to do. Graphics hardware actually has it built in now. You just have to turn it on, right? But since we're in a software rasterizer, we have to do it. So how do we do it, right? What exactly are we going to do, right? And so what we have to do is we have to figure out a way to basically straighten out this curve when we are about to operate on things. So we have to be able to straighten it out, and then we have to flatten it again, right? So we have to be able to kind of like do this curve, in and out, right? And so thankfully, this sRGB, right, has an actual definition. And you can look it up, right, sRGB, where they've actually sort of defined what the curve is. And we're probably not going to be able to use the curve exactly unless we choose to use a lookup table. It'll depend. But we can certainly look at what the curve is defined to be and then try to come up with some approximation thereof. Now, this is a lot more information than probably I would have hoped for. So this has got all of the transforms for how they're computing it. Yeah, so this is a little bit... So basically, if we wanted to do exactly sRGB, which, it's basically a fairly complicated color space transform here, right? They're transforming the colors slightly into a different space, and then they're doing the gamma decode here. They've got the exponents listed, blah, 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 like all this stuff. If we actually wanted to do all of this in a software rasterizer, we'd have to do it with a table, right? We'd have to have a lookup table that translates gamma values. And I don't know whether we want to do a lookup table or not. I don't actually know if we want to do that or not. So let me see if I can find just a standard monitor gamma thing. Because usually what you do is you assume that the gamma is about 2.2. And that's an easier thing that I could sort of show you how we could do in software, right? So, in fact, you can see it right here, right? The equation that typically ends up happening, where is it? Well, they kind of wrote it in a way that I don't love. I'm just going to write it myself. I kind of wanted Wikipedia. I always go to Wikipedia because I want to show some math, and I feel like it always lets me down a little bit, right? Like, you know what I can do? Here's one thing I could do. Here's what I'll point you to, so that you can read about this on your own. That's what I'll do. I'll point you to something that's better than this, because I do know a place. So let me see, gamma correct rendering, Naughty Dog 2010. Here we go. So I believe, here you go. So these are the slides from the Uncharted presentation I think they gave at GDC at one point, where they were explaining how they were doing gamma correct rendering, right? And you can see they drew in that gamma there and all this sorts of stuff. And they kind of show kind of nicely what the math is here, relatively well, I think. Well, maybe I'm wrong about that. Yeah, not going my way today. I mean, here is basically the equation, which is saying, that it's whatever the color value is raised to the 2.2 power. But I was kind of hoping they would just have written it out. And they didn't write out the reverse one. You can see they have it here where they've got the translation, right? So 2.2 and 0.45, which are the powers that you would go back and forth, right? 0.45 is 1 over 2.2. All right, so I don't know. I'll still leave you with this recommendation because I think it's probably a good thing to read. I remember it being a pretty good sort of way of learning about it a little bit, right? And hopefully you can snap this. If you can pause the video or something on the YouTube, you can snap this guy and take a look at it. Here, it's John Habel is the guy's name, and really, like I said, this is kind of the slide that's pretty good here, right? Which is kind of saying like, okay, if you've got, I'm trying to think see if they've got no, they still don't. I feel like the actual presentation had better slides than this. So maybe actually go try to download the actual talk, which I don't know. It should also be up here. Oh well. Well, anyway, I did the best I could. I apologize. So we'll just leave it at that, and I'll move on here. So basically, what ends up happening is, instead of trying to mimic sRGB exactly, which would require a table lookup, what we can sort of do is say, well, this monitor curve is generally expected to be an output of the form POW, right? And don't even have to, I guess, write POW, but I can just say it is the color value, right? Whatever it is, like the R, the G, or the B. So, you know, like R or whatever, to the 2.2 power, right? So the thing that this is actually what's going on when the monitor is going to display things, right? You've actually got it raising it to the 2.2 power. Now the 2.2 power is a little bit problematic, obviously, because it's a POW function. It's actually, you know, raising a color value to an explicit power is a little bit daunting potentially in a software rasterizer. Again, that would be something we'd kind of think about table driving. But what the compromise that I reached with Juan when he was demanding that I cover this on the stream was 2.2 is pretty close to 2, right? So a curve, in fact, we could probably, I don't know if Wolf from Alpha, or I think Google might actually do, graph x to the 2 and x to the 2.2. Can it do that? So if you look at these curves, you know, they're not bad, especially in the range of 1 to 1. I don't know if they have a way of me sort of explicitly saying I want to see just that area. But like, let's zoom in here, right? Like so. And you can kind of see, like, from the area that we care about, from 0 to 1, which is really the color area that we care about, they're really pretty darn close in there, right? You can see they're not bad, right? And so it certainly, you know, Juan, I was basically saying, well, you know, I don't know that I'm going to do POW 2.2. You know, maybe we could table drive it. I'd really like to keep tables out of the software rasterizer if possible, so we're not constantly doing fetches into them, et cetera, et cetera. And so 2.2 was kind of settled on as not being possible, or something I didn't really want to do, but 2 would be doable. And the reason that 2 is doable is because squaring something's easy, right? That's just R times R. And that's an easy computation for us to do. And the inverse, right? Because we need both of these, right? We need to be able to put it into the space and out of the space. So we would need to be able to do R times R, which is easy. And then we need to be able to do square root of R, which used to be actually pretty tough. But nowadays is a lot easier because processors actually have accelerated square root of R pretty well now. Like Intel processors actually don't have that hard of a time computing square root of R because it gets used a lot in like normalization, right? Like you've seen us do it on the stream where we had to do like, okay, we have a vector and we want to know how long it is, right? It's x squared plus y squared square rooted, right? So you need that quantity a lot for normalization or to tell how long things are and stuff like that. So this ended up getting accelerated quite a bit. So R times R and square root of R are things that we could do pretty quickly. And you know, maybe if we're feeling super motivated to try and get closer to 2.2, we could do some fancy numerical stuff there and try to do that. But at the very least, I said, well, okay, that's not that big of a deal. Like, we can definitely handle that. So really all this boils down to is when the artist has the colors, right? When they've put these colors in there, we need to take them out of the space by doing the forward operation to put them into linear space. So we need to basically have right here, right? We need sRGB to linear, right? And then right here, after we're done doing all of our operations, we need another thing, which is linear to sRGB, right? And there's two ways that you could envision this pipeline, and they make sense in different scenarios, right? One way is that the frame buffer itself is linear, okay? So meaning, remember what we're doing here is we start with like a canvas, right? A blank screen. And we start blitting stuff onto it, right? We've got whatever, we got trees and ground and heroes and whatever. We start blitting stuff onto it, right? And all of these things are in sRGB sources. But the question is, what is this? What is the frame buffer, right? Because we have two choices. When we pull things from sRGB to linear, we can write that linear into the frame buffer directly, or we can do the blend on it and then convert it back to sRGB and write the sRGB into the frame buffer. So the frame buffer can either be a linear frame buffer or it can be an sRGB frame buffer, and we have to decide which we want to use, right? In our case, because we're a software renderer, and because we're not doing a lot of 3D constructive stuff, we're taking bitmaps that are mostly finished art, maybe doing a little relighting on them, and then blitting them on top of each other, basically. We probably wouldn't get that much use out of a linear frame buffer, right? So we'd only be talking about the need to sort of, if we were trying to save that conversion to sRGB, right? Which is to say, if we're trying to save these in and outs so that we only do the sRGB to linear, and then we only, we do all our blits on top of each other, and then we only once at the very end take the frame buffer, and when we put it out to the screen, right, at the very end, we'll translate it back to sRGB, right? And so that would save repeated transforms when things, overlap each other, when we're drawing on top of each other. That would save a bunch of out transforms, right? That would save a bunch of linear to sRGB transforms. But my assumption, and I could be wrong about this, my assumption is that mostly we're going to care about bandwidth. And in order to store a linear frame buffer, we would need at least 16 bits per pixel, per channel, sorry, instead of the 8 bits per channel that we're using now. Because 8 bits per channel simply isn't enough to store linear color without banding. And the reason for that is exactly this up here, right? 8 bits are sort of enough to avoid banding when you are in this curve because it puts the resolution where the resolution belongs, which is at the bottom end, right? But if you were to straighten this out, you would not have enough resolution down here to prevent banding. So you need to store more bits of precision in order to actually prevent the banding. You have to go up to 16, right? So I don't want to do that because that would double the bandwidth requirements for our reads and writes to the frame buffer, which I don't want to do, right? Now there are ways we could get around that. There are lots of other things we could consider there. So if we really thought for some reason we really needed a linear frame buffer, it's entirely possible that we could structure our rasters around that. But I don't really think that we need it for anything. So I suspect that what we will want to do is do the in and out on the blit. Because we'll already, because we're a software raster, try to minimize our overdraw by doing some intelligent things probably. And so I think that that's probably just the right way to go. Because that'll save on the bandwidth for us, save on the cache pollution. There's just less in the mix there. And this should be hopefully relatively cheap to do that extra half of the in and out. That's the hope anyway, right? So yeah, so that's basically what all we really have to do. And like I said, try and maybe, if you can take a look at this, this is really not, unfortunately, this is not kind of what I had hoped for. I guess I should try and look for the slides because, I don't know, I want to point, the slides had more stuff on them. And I was kind of hoping to point you to that as an extra resource because I know people usually ask afterwards if there's a thing they can read about. And there is, it's a pretty good presentation. I just don't know where the actual slides are. And I was kind of hoping that maybe someone would find them. Yeah, I don't know. So I'll look one more time. Is there a slides? Here they are. Here we go. Let's see. Here we go. So this is another one. Maybe snap this address if you can to take a look at. Because, yeah, see, there's a lot more slides in here, too. He just had, like, the highlights in the other one. And he shows, like, more examples of things, right? And that sort of stuff. So, I don't know. I feel like it's a pretty good way to kind of get more comfortable with it to look through this whole thing. And he shows kind of like, okay, how it's stored and how it's output and that sort of stuff, right? So, yeah. All right. So what we want to do here, right, is we essentially want to mimic, and of course, again, like I said, I'm not a gamma expert, so you always have to take these with a grain of salt. And if I make a mistake somewhere, hopefully someone will catch me, because I'm not, the kind of guy who does a lot of this kind of graphics programming. But what we want to do is we want to first mimic what the monitor is doing to make uniform brightness out of these values, right? So if the monitor is doing red to the 2.2, right, and we're saying we're going to do a simpler version, which is red to the 2, we're going to pretend that's what it's doing. We want to do red to the 2.2 to get us out of sRGB and put us into linear space. We then do all of our operations that we need to do with math there, Then we do the square root of that, right, to get us back to sRGB space, and we write that down, okay? So it's really, really simple for us to implement this, sort of not full sRGB, but very close kind of approximation, because if we go take our render group and we look at what we were already doing with draw rectangle slowly, if we want to come in here and do that, really all we have to do is take these color values that we were extracting, right? A, B, C, D, right, like that. All we have to do is make a function that's basically like, texel A equals sRGB to linear texel A, right? This is all we really need to do, something that takes them out of here, right? B, C, D. So that will turn them into values that are light linear, right? So this is, go from sRGB to light linear space, or we could call it brightness linear brightness space. I don't know what you want to call it. Maybe we should just, there are some other little tweaky bits, which is like brightness is kind of a measurement that combines RG and B, and maybe you could argue this isn't quite linear brightness, but it's at least gamma corrected, right? So we're not, we're not having that gamma curve in there anymore. So let's call it linear brightness space, just to sort of put some scare quotes around it. Then we do all of our math, which is assuming that it's in linear, right? And then when we are done with that, and we want to write it out, we need to convert them back, right? Now, one thing that's kind of annoying here is these are not normalized values. These are still 255, these are still 255, 0 to 255. And presumably, if we want to do the squaring here, we would really prefer them to be in 0 to 1 space. So we probably also want to do the inversion here. So maybe like we want to call this sRGB 255 to linear 1, right? Because we're going from 0 to 55 to that 1, right? So we'll do that. Then what we do is we'll do our operations in that space. And I believe that if we do it in that space, we can now get rid of some of this, this additional, the 255-ness that we were doing. So for example, SA is actually just correct now. It doesn't need to be divided by 255 because we're now actually correcting that. Our source pixel, when we read that in, right, our dest pixel, when we read that in, also has to be corrected. If our frame buffer is in sRGB space, we need to do the exact same thing there. So if we go ahead here and do a dest, to read that in, when we create that, and let's see here, that needs to be RGBA. Let's see here. So we have R, we have G, G, B, and A. There we go. Is that correct? R is 16, so no. We need R, G, B, A. There we go. Sorry, got to keep that correct. R, G, B, A. Yeah, there we go. Gotta love that Intel, that Windows ordering there. All right, so we get that dest pixel in, and now we need to be able to do that as well, so that we put that into linear space, like so. And then what we want to do is we want to do all of our other operations on that. Now I'm going to go ahead and actually I'm gonna actually go ahead and change the SA, SR, SG, SB stuff here to just be like texel R, texel G, texel B, and similarly like the dest here, we'll do dest R, dest G, dest B. And so that looks about right. Now we actually have to, before we write them out, we have to convert them back, right? So we have to, convert this vector. We're going to have to do something here where we say put this like dest 255 or something is linear 1 to sRGB 255, right? And we're going to have this in some actual space that we can do here, like, this will actually be, I guess, blended, maybe? This will be blended 255. Need some better names for these things. Blended. There we go. And so if I go ahead and make this one now into an aggregate, there's the A, so that goes at the end. Here's the R, the G, and the B. And so that would give me a more correct pipeline. So this is, this is go from sRGB to linear space. This is, and that is as well. And this is to go from that linear space back to the sRGB space, right? So now we actually have to implement those functions, obviously, since we don't have them yet. So we got sRGB to linear, and oops, we got a couple bugs here. That's an A, and then these guys have to be blended 255.A, R, G, and B. All right. So let's go ahead and actually put these in here. So we've got, a function that we want that will turn our color values from sRGB 255 to linear, and then from linear to sRGB 255. So in this case, like I said, what we want to do is create a result here that's going to be squared, right? Just like the monitor would do. And we don't touch the alpha because the alpha is not a brightness value. The alpha is just, the alpha is strictly a value which tells us how much we want to blend as a percentage. And so it only ever operates in that linear space anyway. So we're just going to assume, at least for the time being, that our inputs are in linearly encoded alpha. Although, who knows really? It's hard to say what alpha is encoded in depending on what the program it came out of, and but it should generally be considered a linear value. Like if it's coverage, it would be linear and stuff like that. So R, G, and B values are going to be, just whatever the input was squared there. So trying to mimic what the monitor is doing with that curve, where it's squaring the curve, right? And then when we want to take it out of that, we have to do the inverse of that, right? So we have our result. Our result.r is going to be equal to c.r square rooted, right? Like so. And the A is going to be a pass-through, just like it was before. Okay, and then we return the result. Now, in this process, I said we've got that 255 in there as well, right? And so one thing that we want to do before we do this, and in fact, do I have a squaring function? I usually write one, and I suspect I did. Yes. So we actually should just write it like this. There we go. Okay. So what we want to do here is we want to convert this first, right, to that inverse 255 value, right? We want to be able to turn this into a value that's from 0 to 1 before we square it, right? I said that that was going to be baked into this routine. That's why it's sRGB 255 to linear 1, right? So it does that. And the same is going to be true here, where we want to blow it back out to that because we said that that was how this is going to work, right? And we'll go ahead and do that here. So that way we've got that sort of pre-baked in. Now I believe everything should be kosher now, but I kind of made a lot of modifications there, so we may end up with a totally messed up tree. Yeah, as one might have guessed. So let's go ahead and go through that a little more with a little bit more of a fine-tooth comb and try to make sure that everything is kosher and maybe step through it as well just to debug all of that. So let's make sure that we've got this stuff working properly. So we want to be able to square our values that come in, our RGs and Bs. They go through, and we're going to, I said I wasn't going to square the alpha, and yet I did square the alpha. Let's make sure that doesn't happen. Okay, there we go. So that's fixed. So Right. We don't want to square the alpha. We just want to square the color values, and we want to square them after they've been converted to the range 0 to 1, right? So we can do that. Now, we don't necessarily have to do that. What we could do instead, we could still do everything in 255 space, I suppose. I'm guessing that since we're going to have to do that multiply either way, we might as well do it first. What we could do is square them and then multiply by the inverse of 255 to scale them back down to 0 to 255, but it just seems like you might as well put them to 255 first so that you can do all your operations in the 0 to 1 range, which usually makes it a lot easier. So anyway, I also think, I can't remember if there's, well, no, I guess there might not be any accelerated ways in SSC to do that. You may just have to do the standard multiply. Anyway, so, off we go. That looks okay to me. The result here is doing that sort of, putting that 255 back in there, which is what we want. And it's passing the alpha through, which is also what we want, because we don't actually want the alpha to be touched in any way in terms of modifying it there. Oh, that's not right, though. I still want that in there. Oops. C.A. There we go. And so let's take a look at the rest of it here. Draw a rectangle slowly. And we'll go to about 6:15 today, since we started pretty late. Where are we? All right. So we grab our texels out. There's our texel pointers, A, B, C, and D. Man, we've got to stop. I've got to stop those assertions. They're killing me. So I'm going to go ahead and just say that we're not going to assert on those anymore. We proved we didn't fetch outside the texture. So we'll just take those guys off for now. We'll leave on the asserts for the other stuff. All right, there we go. So we read out our textures here. We get our texel A, B, C, and D exactly what we did before. We didn't touch any of that. We map each of those from the 255 space to the linear space because they are in the 255 0 to 255 space, which needs mapping. So we map them out. We then do the bilinear blend, right, between the texels by doing just a straight linear blend. We didn't touch any of that. We grab the texel A, B, C out there, although I guess we were saying that sort of, I don't know why we actually were doing that. Let's just plug this right back in there. There we go. So let's see here. We grab the texels A times that color A, which is which is that value that we were getting passed in case we modulate, which should just be 1.0 at this point. Although I guess we don't know what that color value actually is. Presumably it's in that space though, right? Color, yeah. So those color values are coming in the 0 to 1 space as well. So those are all fine. We grab the dest out by reading from the pixel into, let's see, R, G, B, and A, which looks right. And then we need to convert that from sRGB to linear. So we do that. We then take our destination alpha, which is here, and we compute the inverse of the source alpha. We multiply the inverse source alpha times the dest red. We add the texel red that we had sampled. Same thing with the G and the B. So that's a 1, that's an inverse source alpha 1 blending mode. We then compute using RSA and RDA the final values. Oh, so this is not good though. This 255 should not be in here, right? That should not be there. That was that was old. Let's get rid of that. We then convert back to sRGB space by taking our blended 255 there, which should multiply by 255 and get our colors back for us. And then we go ahead and pack in our A and our A, our R, our G, and our B into pixel. So that seems like it should be relatively straightforward. I'm assuming that we must have some kind of typo there. So I'm going to go ahead and just set a breakpoint so I can watch and see what happens in there and see if I can't spot what goes wrong. So here we go in the routine here. And it should be hopefully pretty easy to spot what goes wrong because, I mean, it's all black. So any pixel that's getting computed is basically wrong, right? So let's take a look at what our texel values end up actually being, right? So if we take a look at our texel values, they are correctly in the range of 0 to 1. So that's good. And hopefully all of them are, right? That one is as well. Texel C, texel D, right? So all of those guys are in the range 0 to 1. You can see there. So at least we know we're loading them and operating on them in sort of a reasonable way for the sRGB. There is our blend, our bilinear blend. Let's take a look at what our RSA value is, which is going to be our source blend, which is 1. So our source is, I guess, that's kind of odd, don't you think? Why? How is that the case? Hold on a second here. What is our texel.a and our color.a? Wait a minute. Why would our color... Did we really stop on a pixel that has a color value of 1? An alpha value of 1? That's kind of weird, don't you think? I feel like the first pixel that we encounter should have an alpha value of 0 because it's going to be on an edge. Maybe this isn't the first one? Let's find out. Ymin 203, 80. Oh, so this isn't. Let's do it this way. I wanna see somebody who's I want to prove to myself that we've got an alpha value of 0 at that first pixel that we hit. So let's take a look here. So just to make sure, although that could have been just the first one that was included, I suppose. All right. There we go. Okay, so we're all zeros here, which is good. So this should leave the destination intact, which we know it isn't. So again, we should be able to see why it isn't, hopefully relatively easily. Our RSA value is 0. What does our dest look like? This is reading out of the frame buffer. It's that lovely purple color. I'm not sure how it's at that lovely purple color. That's a bit odd to say the least, because it shouldn't be that purple color, right? The only time this should be drawing, it should be drawing on top of valid stuff. So I guess it's because, oh, the very first frame, I guess it wouldn't be because we haven't filled our ground patches yet. So okay, I can believe that for now. All right, so we do our sRGB to linear, which again converts those to what they should be, which is 1s. We compute our inverse RSA, which is 1, and so that should leave us with basically just the dest and nothing getting added in, right? So our blended should basically be equal to the destination there. So there's the dest, there's the blended, and that is exactly what they should be, looks like. And then we're going to do our linear to RGB conversion. And so that should give us values in the range of 0 to 255. And it totally did not. So what got messed up there? What is the problem? Ah! Well, that serves me right for being hasty. You can see what the problem is here. I wanted to square root them before I multiplied them by 255. But I actually was multiplying by 255 first because I was just kind of like mindlessly typing that in. So that's no good. Definitely not good. That may be our only bug. Let's find out. We don't really know, but we'll find out. So there is our tree. You can now see in all its gamma corrected glory, our tree sort of rotating around there. Of course, we don't really have any good tests at the moment to test whether we're gamma correcting properly, so I guess I don't know for sure that we actually are, but we are at least going through the correct pipeline now. We're actually doing sort of the map into the space and the map out of the space, so at the very least, Juan will not have to lose any sleep over it. But again, like I said, it's not the kind of thing that I've ever really seen a difference for in 2D sprite composition. I've even seen demos where people say that it makes a difference, and I didn't see the difference. So I'm not anticipating this really doing anything for us. I'm sorry. I apologize to people out there. Like, I totally, for HDR and 3D rendering stuff, I'm totally on board with the gamma. It definitely works, and it's definitely important. But for 2D compositing stuff, I've just never seen the effect. And so, I mean, the only place you're going to see it is where we're actually doing blends between relatively disparate colors. And, I don't know. So again, we may not have done it quite correctly. Maybe we've got a bug in there. But even so, it's just like, I don't know that there was that much wrong with the original way to begin with anyway, so I'm not sure that there's really all that much to get excited about. What we could do is we could have a little toggle that allows us to switch it on and off potentially, and maybe see if it makes a difference. I don't know. But again, not really expecting much out of it. But anyway, that is the gamma. And you do want to know this. It is good. I mean, Juan is correct. I should show it because it's something you do need to know when you start to do some more fancier effects that maybe you don't do as much in 2D stuff, but that you would do in 3D. It's important. And so now we've got it out of the way. At least we know it's in there, and we can make sure our pipeline handles it well enough. And so there you go. We'll have to talk about how we're going to optimize that when we get to the optimization stuff, because now we've got to deal with the square root in there. But it's, like I said, it's not that big of a deal to handle a square root nowadays. It used to be a big deal, but it is not so much anymore. So that's really it. I guess we won't even need the extra time that I said that I would take. But that's really all there is to it. That's the majority of it. So we pretty much just have to do that slight bit of work, and then we're good. Now, maybe what I'll throw in at the end here, since we do have about 10 minutes before our hour is up, what I might do is let's go ahead and take that color value that's getting passed in here and actually use it. So draw, we call it draw rectangle slowly. What I'd like to do is say, okay, when we pass this color value here, that's not the color value, sorry. When we pass this color value here, let's actually start using that, right? So what we can do is we can do sort of a modulation of the color, right? We can multiply the color values that come in with the color values that we're reading to tint whatever it is that we want. So for example, right, if I have something, this is pretty straightforward, right? But if I have a certain amount, if I have the RG and B of the texel, right, that's coming in, if I want to tint this, I can introduce coefficients like CR, CG, and CB, right, that multiply these values. And if those coefficients are 0 to 1, I can control how much blue, how much green, and how much red I read out of the texture map, right? So it's pretty free for us to add a thing that allows us to tint our texture maps by just allowing this color that we were passing in to draw the rectangle with as a solid color before. We can just use that to actually just multiply the colors as they come in, right? It's really, really straightforward for us to be able to implement something like that. All we would have to do is introduce here a place where we multiply the color values together, right? Like so. Because we're already multiplying in our inv RSA, we are already multiplying, oops, that's the dest, sorry. We're already multiplying by that color alpha value. So we're already doing something where we're taking into account the pre-multiplication of it. So all we really have to do here is just multiply the color values that we read out of the texel by those colors that are input, and then we can tint, right? Or at least we should be able to tint. So if you take a look at what happens there, right, where we've got our tree, let's get our tree up there, and then I'm going to go ahead and allow ourselves to sort of do it, the live code editing that we so love here on the show. So if I do that coordinate system thing here where we're passing that color, I'm going to go ahead and pull that color out into something that we can see a little bit more directly. So here it is, right? There's the color. There it is. So you can see we've got some kind of crazy stuff in here with still an alpha of 1.0. So if I go ahead and compile that, we can now play around with this pretty easily. We could call this color angle, and we could make sure that it oscillates a lot more frequently, like maybe that is 5.0 times the angle instead of, so it just it cycles much more frequently. And there you can kind of see, right, a much sort of clearer demonstration of tinting those textures, right? Like, so we can just put a modulation in there. It's pretty much free. It allows us to kind of play with the RG and B values after the fact, which will probably be something that we'll want to use If not for normal stuff, although a lot of times you do use tinting like that for normal stuff. If not for normal circumstances, at the very least for like special effectsy kind of things, maybe where we have sort of like sprites that want to be like bullets, or special effects that want to get tinted certain colors to depend on what the effect is. That's a pretty cheap way, again, to get more out of your art there by allowing them to be kind of freely tinted. And again, that's an easy thing to do. The hardware does that as well, so it would translate directly over to OpenGL and all that sort of stuff. So again, that's a pretty easy thing we can throw in there. And then, wow, we still got 5 minutes left. So I don't really know. I guess we'll just go to the Q&A because I don't have really anything else short that I want to start talking about at the moment. But that's pretty much it for the gamma and the color stuff. I could also, I guess, vary. If I throw in here the alpha value, I could sort of vary the transparency of it, and we could see if that works at all. That seems to be working. Yeah. Looks like it. Now, of course, one thing that I guess we didn't do is we're not pre-multiplying that alpha properly. So if we change, here's the thing I was thinking, right? We're handling the alpha by multiplying the alpha by the texel A. So our destination, we will use less of the destination as this goes to 0, right? So it can fade out our sprite. But really, these values don't go to 0. I'm sorry, it uses less of the value because it's inverted. It uses less of the value as this goes to 1.0, if the texel was 1.0, right? But these colors here are supposed to be pre-multiplied by alpha because we just add them straight in, right? If you remember when we talked about pre-multiplied alpha. And maybe I'll use the remaining 4 minutes to talk a little bit more about that. These really want to be multiplied by that color A as well, right? Because they have not been yet. So really, this should, in fact, be in here like so, in order to get the correct equation for the blending. So now we're good. Now we're blending correctly, right? At least I believe we are. That is a really weird tree. Let me go ahead and make that oscillate a little bit more quickly. There we go. So anyway, let me briefly mention what I did there just so that people understand it. So what we were doing is we were doing pre-multiplied alpha, and I talked about the importance of that, which is basically because much like the gamma, pre-multiplied alpha is the only kind of alpha that properly works through linear blends, right? So when you're doing linear blends and stuff, you need to be pre-multiplied alpha because post-multiplied alpha or non-pre-multiplied alpha, it's just not pre-multiplied, not post-multiplied, but non-pre-multiplied alpha does not actually work, as we talked about before. So what was happening there is we have an equation, right, for like each of our channels, which was 1 minus the alpha times the dest, right, plus the source, because we're assuming that the source is already multiplied by the alpha. This is this equation, 1 minus a d plus as, right? Assuming that the as was already collapsed into the s, right? So it's really s prime, right? It's like s prime equals as. And so when we added another color in there, if I was to take that other color we had modulated in there, well, we essentially didn't take into account the alpha of that color, that second color that we were doing. So we had, what I had written inadvertently was 1 minus a d, plus sa s prime b, where the color that came out of the texture, right, this is the texel, that was pre-multiplied, but the color that came from the function was not. And so when you multiply something that's non-pre-multiplied with something that is pre-multiplied, you get like a half and half result, right? So what I actually wanted to do was make this s prime a, right? I wanted to multiply the source color by its own alpha first, right? And so that's all I did, to make sure that all of the alphas were pre-multiplied in the pipeline. All right, with that, I think we can go ahead and go to the Q&A. There we go. What would be the visual artifact of using 2 instead of 2.2 for the gamma? So the answer is nothing for what we're doing, because there isn't even a visual artifact for not doing the gamma at all, as you saw. So really the reason, it's basically, if you look at this curve, right? So, here's the actual curve, right? This is the 2.2 curve, right? And here's the 2.0 curve, right? Those are the two curves. Let's say here's 1 and here's 0, right? And here's, max brightness. Or something. And I guess that they both cross at 1 because of the properties of raising things to powers. So that's not quite accurate there. So let me go ahead and kind of fix that a little bit, right? So basically the only visual artifact is things are a little bit darker than they should be if you're using the 2.0 instead of the 2.2, right? Because when you're bringing those things up to linear, you're not quite getting them, you're not quite pulling them back to exactly linear. You're pulling them back to almost linear. So I don't even know if you could perceive that difference. To be honest with you, I don't know. But I would suspect that it would be a very small difference in most circumstances, if there was one. So it's not a huge deal. Garlando Bloom says, also need to do additive color tinting for full expressiveness. Well, Garlando Bloom, that is one of, well, I guess if you want additive, like, so you want to be able to add in red where there wasn't red before, basically. So there's a plus, there's an addition in that. I don't know how I feel about that. I mean, how would you, well, all right. I mean, maybe we'll think about it. We'll think about it. I have a CS background, but I'm 2 months behind on coding this. It is much easier to follow when I'm not trying to type myself. How detrimental would it be to my understanding to watch and just stop coding if I get too far behind? Sometimes when you're moving things around, I have to watch that bit 2 to 3 times. I don't know. It's a good question, but I don't know the answer to that question. I mean, one of the problems is that if you don't do things, you tend to not really learn them. So I would say it's probably not a great idea to not try to actually do the code. Because remember, there's no such thing as keeping up with Handmade Hero. It's a video series. It's going to last a fixed number of hours. I don't know how many that's going to be. 500, 600, something like that. And that's going to be over. And so you will have your entire life to catch up with it if you want to. You don't have to stay up to date in any kind of real sense. So I would say just take it at your own pace and don't worry too much about being up to date. You can always ask questions on the forums. You don't have to ask questions live. Would it be worth only using gamma correction on texels that have an alpha not equal to 0 or 1? So technically no, because we're doing a bilinear blend between texels. So technically those texels want to all be gamma corrected as well, so that bilinear blend will work. So, we're doing this for one, and so, maybe we'll just have it so you can compile out the gamma correction if it actually makes a difference speed-wise when we actually profile it. But, we put it in there for now. Robot Chocolate Dino says, could we do our maths in sRGB space? So the answer is you could, but if you were going to do them in sRGB space, they'd look like a bunch of power functions, right? Because your linear blend is now, like, the definition of your linear blend is actually right? Because, okay, so here's our current lerp. Our current lerp for a, t, b, right, is 1 minus t, a plus t, b, right? That's what we're currently doing. If you wanted to make a linear interpolant in sRGB space, well, we know what it actually is. It is this function. It is with our approximation, it is the square root of 1 minus t a squared plus plus t b squared, right? So, you know, I mean, you could write your lerps that way always, where you square a and you square b, you do the blend and then you square root them. But it just would be way less efficient to always do the math this way instead of doing it just once at the top to get that squaring and then once at the end to do the square root. You know what I mean? So it just doesn't seem like you'd ever want to do the math in sRGB, but you could. You just have to do the translation every time, if that makes sense. What's kind of interesting about this is this kind of is like I'd never really thought about this before because I never really looked at what happens if you simplify gamma down to square and square root, which is what we're doing here. But this is kind of interesting, right? Because it looks like a triangle, right? It looks like this, where lerp is here, and you know, this is 1 minus t square rooted a, and this is square root of t b, which is just kind of interesting. I don't really know. I don't really know if that has any ramifications. But it kind of looks like that, right? I mean, so let's say that I had this triangle, right? And I wanted to solve for lerp. And I know I have a side that's this and I have a side that's that, right? Well, I know that I would take, you know, a squared plus b squared square rooted is the formula, right? So plugging those in, I would get, you know, 1 minus t a squared, which is just 1 minus t a squared. And I would have, you know, root t b squared, which is just tb squared. And I would add those together and square root them, Pythagorean theorem, to get my lerp. So it's kind of interesting that it looks that way. I'm not sure that there's really anything special about that, but it's kind of interesting, right? It's just one of those things that catches your eye when you see it. I wonder if you could translate the lerp so that you just did the operation on the t value, if that makes sense, and didn't actually have to square the a or the b. I don't know if what I'm saying makes any sense, but basically, like, I'd be interested to know if you could turn this into something where you could get the equivalent of this out by just manipulating the t values. I don't know if you can or not. Let's just, you know what? Sorry, I think maybe this Q&A just turned into an exploration. So let's say we've got this here. So this is our f of t. I'm just going to shorten it so I can write it easier, but it's really f of atb equals that. So let's square both sides. We'd get f squared t, right, equals 1 minus t a squared plus t b squared, right? And I feel like the problem is you're going to get this cross term in here that there's nothing you can really do with, you know? Yeah, well, let's keep going. F of t equals a squared minus t a squared plus t b squared, which is, of course, the familiar, excuse me, which is the familiar a squared minus t, or sorry, plus t b squared minus a squared, right? So yeah, I don't think there's much you're really going to do with that, unfortunately. Yeah, I don't see that really helping all that much is the thing. If you could get it so that the t would move outside, but I just don't see how that's going to happen. I mean, then you re-square root it, right? I mean, I guess I really didn't need to square root it in the first, I didn't really need to square it in the first place because it's all under the radical anyway. But you've got a squared, right, plus t b squared minus a squared, and you still can't pull that t out in any useful way. Like, you want to move this out here if you could. Yeah, I don't know. It's kind of interesting. Anyway, I'll go back to Q&A. When are you going to start implementing OpenGL for the rendering? Well, probably not until we're done with the software. Like, we'll do the optimized software renderer, but OpenGL is just kind of there for performance. But you know, we won't learn a whole lot by implementing OpenGL, so we're not really focused on that. Wouldn't the 10-10-10-2 format, which is available in hardware, be sufficient to avoid banding? Well, so the 10-10-10-2 format, I mean, really, it depends on what we end up doing with our frame buffer. So if we end up using destination alpha in the frame buffer for translucency, 2 bits for alpha isn't going to cut it. So, you know, we could use something like 10-10-10-2 or 11-11-10, for example, with no alpha in the frame buffer. We could decide to try and do something like that, and that might be enough to avoid the banding. But we would be sort of boxing ourselves in because then we wouldn't have any way to do destination alpha, right? And so that's a little dicey. I don't know that I would want to go down that route if we didn't have to. What is the point of using 2.2 at all? Why not just use 2 for gamma? Because it's less accurate. I mean, the answer is you can just use 2 for gamma if you're in a pinch. But if you wanted to be 100% accurate everywhere, you want 2.2. And so when you're in a situation where, like, hardware, for example, uses CLUTs oftentimes, they use color lookup tables for this, I believe, they can just do exactly the sRGB profile, so they don't have any of that wiggle room. But yeah, the answer is, I think 2 is probably okay for a lot of uses, and I believe a lot of people have used 2 as an optimization before. So we're not like doing that. That's not like some new thing we're doing. That's like, I believe that's an accepted optimization of like, yeah, it's close enough, right? By repeatedly converting between linear and our approximated gamma space when doing each blend, are we compounding our errors? So, you know, yes and no. If we thought that if we were accumulating, so you have to understand, what do you mean by errors, right? So if you take a look at what's happening on the screen, a lot of stuff is just the result of the final pixel that gets written there, and there isn't a lot of translucency that's happening. So the only time that you really end up with seeing the result of repetitive blending is at the edges of things, or when there's a thing that's like translucent, like or semi-transparent, I should say, not translucent. Translucency is a different thing. Translucency is like a superset of transparency, so forget I said that. Something that's like semi-transparent. So, you know, we really won't have that much error to compound. But you're right. For things where a lot of edges were overlapping, we would be potentially compounding our errors there. We'd have like 1 bit of rounding error that would happen each time, potentially, for example, right? But at the end of the day, I don't know that that really is going to add up to all that much. But that is one motivation for why when you're starting to do things like trying to do photorealistic rendering and stuff like that, you will keep all your stuff in floating point so that you have a lot more bits of precision, so that you don't fall into, you know, traps like that where you might end up with something that looks a little wrong, gets a little banded or something because of it. We just don't have that kind of scenario happening, so we really don't have a situation where we're going to need to worry about every little last bit of precision, because we're just not doing stuff of that nature at the moment. Do all monitors use the same 2.2 curve? No, actually they don't. And in fact, that is why you get these things, which are like color calibration curves for your monitor. The fact is, and I guess this might be another argument for why 2.0 might be good enough. 2.2 is not exact. 2.2 is an approximation of what most monitors are trying to do. Not all monitors are doing that. Not everyone has their monitors set up the same way. You know, the contrast on the monitor may be set differently. There's all these other things. And you will often see stuff where people will actually try to figure out what the gamma curve is for a game. If you've ever seen something where a game comes up and says, adjust this knob, which is like a little thing on the screen, until these gray colors look the same. If you've ever seen that, that was them trying to figure out what your monitor gamma was, right? So yeah, there's no perfect solution for it. It's one of those sad facts of life where you just don't get the information that you need to do the perfect solution. So, you know, again, that's why using 2.2 is probably not that bad of a compromise, because it's much better than not doing gamma at all, but it's probably not that much more incorrect than doing 2.2 for most circumstances, I would suspect. Not a gamma expert, I'm not the guy to ask, so that's just my supposition. You would have to ask somebody who is a little more hardcore about it. Is raising the color value to 2 instead of 2.2 really going to save that much processing power? Yeah, actually, probably a ton. Because the difference between squaring something and raising it to the 2.2 power, like squaring something is like one extra instruction. It's one multiplication. But getting it to the 2.2 involves a ton of extra, like many more instructions, right? I don't know exactly how many. We'd have to actually go work it out. But when you're talking about the difference between one instruction and many instructions, like even let's say it was only 5 instructions, when we're talking about something we do for every pixel on the screen, you cannot afford 6 times more expensive, right? Like that's what that would be, right? 6 times as expensive, I should say. So yeah, 2.2 is a lot more expensive than 2, as it happens. But that said, that's me saying it as if you were going to implement it like POW. So it may be the case that if you worked out a good approximation specifically for 2.2, that you could get it down to not very many instructions, but I doubt it would be as fast as one instruction, which is probably all I'm willing to spare for gamma, probably, I would guess. But, you know, who knows? And again, it's not just the raise to the 2.2 you have to do. You have to do the 2.2 root, right? The raise to the 1 over 2.2 power to map it back. So you're paying it on both sides, and you need a good approximation on both sides. I got stuck implementing a bit shift plus PRNG in our engine. Thanks for showing a code comment about Wang hashing earlier, which was just what I needed. Well, very glad that Wang hashing helped you out. Let's see here. All right, so I think we're all good. Looks like the end of the questions. So I will wrap it up for today, right on time, in fact. I guess we're a little bit over, but that's no problem, no biggie. So all right, let's close down. Let's close down. That tree is getting increasingly trippy. It's a very, very bizarre tree all of a sudden. So yeah, I would recommend doing some more reading on gamma. Because again, Handmade Hero won't be the place to really see gamma in action because we're just not doing anything where gamma is going to matter, I don't think. But now that you know about what it is, I would definitely say go do some light reading on it just so you kind of get a feel for it, because it's something that you want to know for when you're working on 3D stuff or when you're looking at some things that maybe where it's important. It's good to know so it's in the back of your head and you can go, oh, wait, what I'm doing right now might be affected by gamma. Let me make sure that I'm doing it right. That's just a good thing to know, and every graphics programmer should know it. So thank you everyone for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. We did gamma today. Thank you to Wan Chun for forcing the issue because it does need to be talked about and people should know what it is. And honestly, I was going to skip it because it just wasn't the sort of thing that's going to make much of an impact on our game. But, you know, it's not always about just doing what makes an impact on the game. It's about trying to teach people what they need to know to make their own games. And maybe your game isn't exactly like Handmade Hero. So at that point, it is good for you to know these sorts of things, that they're out there, and you can go take a closer look at them if you need to. So if you would like to... Oh my goodness. I'm having... That's the first time I think my phone has ever rang on the screen, on the stream. I forget that my phone can be rung on the laptop, which is very kind of disquieting. All right, sorry. If you would like to follow along at home, you can always pre-order the game at handmadehero.org, and you can, excuse me, you can get a link in your email, which will allow you to download the source code, and you can play around with it and do whatever you want to do while you try to learn sort of you know, from the stuff that we do on the stream. And sometimes it helps to be able to play around with the code because that's just a good way to learn and a good way to sort of practice for when you need to write your own stuff. So you can do that on handmadehero.org. We also have a Patreon. If you want to support the video series, you can subscribe there. It's always very appreciated. There's forums where you can ask questions, and it also has ports to Mac and Linux, stuff like that. It's a good place to go if you're trying to learn from the series. We have a tweet bot that tweets the schedule, so if you want to catch this series live, it's a great place to go. Yeah. We will be here at 5 p.m. Every day this week. So if you want to come back and see us again, we'll be here at 5 p.m. Tomorrow on Twitch. Love to see you here when we will maybe start talking about how to structure this rasterizer for actually getting some performance out of it. And that will probably open up a whole bunch of cans of worms, including sort of some performance analysis stuff that we sort of have been needing to talk about for a while. So I highly recommend checking it out. I think it's going to be a fun week. And we'll do some interesting stuff. Hope to see you there, and have a good Tuesday either way. Thanks for tuning in, everyone.